We'll see how to obtain the PSD or power spectral density of addition of two random processes. Let us consider two independent random processes, namely x of t and y of t, and we are going to add these together and is represented by the equation below. That is, w of t is a third random process created because of addition of two random processes or independent random processes x of t and y of t respectively. If one or other of the random processes, that is participating random processes x of t or y of t, possesses a mean value or has a mean value of 0, then the addition of their autocorrelation function is given as below. So it is autocorrelation function of w is equal to autocorrelation function of x added with autocorrelation function of y. It's very clearly visible that if you add two random processes, even their autocorrelations will be added to give the resultant autocorrelation function. Because the Fourier transform of a sum is the sum of Fourier transform, it is equally likely or follows that in case of independent random processes with a mean 0, if they are added together, then what happens to their PSD? The power spectral density for the resultant sum is equal to the sum of the individual PSDs or power spectral densities of the participating random processes x and y respectively here. By this definition, mathematically we can represent this by the PSD of the sum, that is w, is equal to PSD of x plus PSD of y. So the resultant random processes or a process w, its power spectral density can be simply obtained by adding the power spectral densities of the individual random processes which are being added together. Likewise, we can also see what happens to the power spectral density of multiplication of random processes. So, how to obtain the power spectral density of the random processes when they are multiplied together? The nature of x of t and y of t, or the two random processes, are independent and then they are multiplied together. The resultant product of the two random processes x and y is nothing but equal to w. So autocorrelation functions also multiply, and the autocorrelation function of w, resultant product w, is equal to autocorrelation of x multiplied with autocorrelation of y, where the time difference equal to tau. Just look into the simple steps of derivation of an expression for power spectral density of w of t, which is nothing but the product of two individual or independent or random processes. Therefore, the power spectral density of w denoted by s omega, sw of omega, is equal to minus to plus infinity. We need to integrate this entire term rx of tau into ry of tau into e to the power of minus j omega tau into theta. So in this expression we can replace for ry of tau, retaining the remaining terms or rest of the terms in the equation as they are. Sw of omega is equal to integration from minus to plus infinity rx of tau multiplied by, we are having second term is ry of tau First one is Rx of tau and Ry of tau. These are nothing but the autocorrelation function of x and y respectively. We will replace an autocorrelation function for y, that is Ry of tau, by the following expression, which is nothing but the Fourier transform. So this is equal to 1 by 2 pi from integration from minus to plus infinity. So y of u multiplied by e to the power of j u tau du. The entire term, which is highlighted with in the square braces or bracket, belongs to Ry, or the autocorrelation function of second random process y, multiplied by remaining term e to the power of minus j omega tau. Let us interchange the order of integration here, thereby shifting s y of u to the first place and Rx of tau to the second place within the second integral, and remaining terms of exponential terms are grouped together, e to the power of j u tau du e to the power of minus j omega tau d tau, nothing but equal to 1 by 2 pi integration from minus to plus infinity sy of u minus to infinity. Again we integrate for Rx of tau and group together the exponential term, which is resulting in e to the power of minus j into omega minus u of tau d tau into du. Now we can observe that the second term, which includes Rx of tau into e to the power of minus j omega minus u into tau d tau into du, is nothing but equal to the power spectral density of x with argument omega minus u. In the first term, sy of u stands to be the same, and 1 by 2 pi is also outside the integration. So therefore the power spectral density, whatever is there, of the resultant, that is random process w, which is obtained by taking the product of x and y random processes, its PSD is denoted on LHS SW of omega. This is equal to 1 by 2 pi into the product of the power spectral density of x multiplied with power spectral density of y. Therefore the PSD of the product of two random processes represented by W of t, we take the power spectral density of the resultant product of two random processes, it is nothing but the convolution of the PSDs of x of t with y of t, which is multiplied by a factor of 1 by 2 pi. So therefore when we multiply two random processes, then their power spectral density can be obtained by taking the convolution of linear convolution of PSD of power spectral density of first random process x of t with the second random process y of t, and which is further multiplied by 1 by 2 pi. And this is it about how to obtain the power spectral density when two random processes are added and when two random processes are multiplied. So for both the cases we have seen how to obtain the PSD, and thank you very much.